Welcome to another instructional video for our Pre-Calculus 11.0 course. Today's video we're going to go through the process that you can use to determine the equation of a quadratic function from a graph or from being given some key points that could lead you to draw the graph of it, or there could be a table of values as well. Anyway, there's a variety of ways that we're going to look at how to determine the equation of a quadratic function. This will be a bit of a review for those of you that work through your Foundations 11 program prior to this one. But again, like most things, we will assume that none of you have seen any of this material before, so we'll kind of work our way through it right from the beginning. Alright, so if you're going to find the equation of a quadratic function, there's going to be two key things you need to know. You need to know the vertex, and you need to know any other point on that parabola. Now, sometimes that information, so they say, well, how do we get that information? It might come right out in the question and tell you, given a quadratic function having this vertex and this point on it, determine its equation. You might have a table of values or a table of data that you're going to analyze, or there could be an actual picture of a graph there in front of us. Now, sometimes this stuff, this sounds all nice and easy, but sometimes you've got to do some digging and thinking to figure this stuff out, which is good. I really enjoyed this section because it shows you some real nice practical applications of quadratic functions. Okay, so to do this, we're going to work from vertex form. Always want to work from your vertex form. So remember, in your vertex form, h and k is your vertex, a is your stretch factor. Now, what sometimes students fail to realize with functions, whether they're quadratic functions or linear functions, is the whole notion of what does the x and the y mean? What does this and this actually represent? Well, x and y, I think we all know, are ordered pairs. And in any type of function, the x and the y represent ordered pairs that satisfy the conditions of that function, meaning that if you drew the graph, those ordered pairs would actually be found on the graph. And I'll kind of talk more about that as we get going through here. I'm going to show you two ways to do this. So the first one, we're going to use a strategy called substitution. And we're basically just going to substitute everything that we know into our function. So to get your quadratic function, you essentially need to fill in a number here, here, and here. And once you have those three numbers filled in, then you would have your quadratic function. Well, hk is given right here. So this would be, the information is directly given in the question. So if I just look at this ordered pair, 5, -17, and what that means is if you were to draw this quadratic, it would pass through that point. Well, what that's telling you then is a value of xy in the function, and this is telling you h and k. So let's think about that. If I knew the x and the y, right, x, y, there's y, and I knew the h and the k, there's h, there's k, well, that would let me substitute everything for those four, and the only thing left would be the a, and that would let me figure out the stretch factor. So this is a way to substitute and calculate the stretch factor. Alright, so here we go. Let's take, so the y value is this one, is -17. My stretch factor is unknown. The x value would be 5. The h value would be, h is the x value at your vertex, so that would be a 3 squared. And then the k value is a -5. Now, it's surprising the number of students that do this properly, but then they can't rearrange this properly to figure out the a value. Well, the first thing you'd have to do is add 5 to both sides. So that's going to take us down to -12 equals a. Now let's figure this out. 5 subtract 3 is 2, and then square it, you're going to get a 4. Well, now to get a isolated by itself here, I would have to divide both sides by 4. And I get negative 3 is my stretch factor. So therefore the answer, the quadratic function that would meet this criteria, have this vertex and cut through that point, would be this one. Y equals a x, subtract your vertex, x minus 3, don't forget it's quadratic, squared, and then minus 5. There I have it. That's a quadratic function that meets the criteria that was laid out in the question. Now you got to sometimes watch your instructions. It may say determine the equation of the quadratic function in standard form, which is fine. We wouldn't do anything any different except when we got to here. Remember, standard form is ax squared plus bx plus c. So then you'd have the extra step. So this is vertex form. If it doesn't say which form, well then we'd stop here because this is a quadratic function. But if it did say to put it in standard form, well then I'd have to do this little bit extra calculating. So negative 3, square your binomial, x squared, subtract 6x plus 9, subtract 5, negative 3x squared plus 18x, negative 3 times 9 is negative 27, and your negative 5 at the end. This would be standard form. Now please make sure you understand, you don't have to do this unless you're asked specifically in the question to express your answer in standard form. I'm just showing you what you would have to do if it had explicitly stated put your answer in standard form. So that's it. That's how you find the equation of a quadratic using the substitution method if you know the vertex and any other point besides the vertex that's on the quadratic. Substitute it into your vertex form, determine your stretch factor, then fill in your a, your h, and your k. You've got your quadratic function. Okay, so that's one way to do it, that's probably, I'm going to say, the way that 95% of the students will do it. There's another way you can do it that's a little quicker, but you've got to make sure you really, really understand what you're doing if you're going to go to this one. I recommend you have strategy 1 mastered, and then if you're kind of starting to feel comfortable with this, I'll show you this other strategy that it's a bit quicker, but as I said, it requires you doing a little bit more thinking kind of in your head. So we're still going to go to vertex form in this method. And it's called the inspection method. That means just by looking at it, analyzing it by looking at it. And what we're going to do is we're going to just leave that empty for a second, our a value. We're going to fill in our h, and we're going to fill in our k. Now I'm going to actually write the stretch factor here just by looking at this. Now I put this picture and table of values here just to refresh your memory on the base. This is your base parabola, y equals x squared, which has a stretch factor of 1. Now we know from the last, we already did the work, the stretch factor for this quadratic is a negative 3. So how can I get that just by looking at it? Well, if you look at this quadratic, looking from your table, if you go one, so here's your vertex. If you go 1 to the right of it, notice you go up 1. If you go 2 to the right of it, you go up 4. If you go 3 to the right of it, you go up 9. You say, well, how do I know that? Well, because the y value on the base parabola, y equals x squared, is always the x coordinate squared. And if your vertex is at 0, so I could go 7 to the right. If I go 7 to the right, it's not in my table, but I know that I should be going up 49 because 7 squared is 49. If I was at, now it works the same going to the left. If you go to negative 2, you still square your x value, which would give you a positive 4. That's why negative 2 and 2 will have the same y value. Let's suppose the x coordinate was at negative 10. So if I was 10 to the left of the vertex, well, 10 left, I should be up 100. You say, how do you know that? Because 10 would be the x coordinate, or negative 10 would be the x coordinate, and then to get the y coordinate, I would square it. So negative 10 squared would give me that 100. Well, when you do it by the inspection method, to get your A value, I'm just going to put a little, so the A value is equal to, I'm just going to put this in words, what is actually happening, you'll see what this means in a second, okay, what is actually happening, divided by what happens on the base parabola, and the base parabola is the one above, y equals x squared. Alright, so let's put this into play here and see how that applies to this one. So let's go up to this situation and let's see what's happening. So your vertex is at 3. The point I'm given is at x is 5. So ask yourself, how far away is that horizontally from the vertex? So if you're at 3 and you go 5, would you agree that that's right 2? So on the base parabola, if you go right 2, you'd be at positive 2. You should be going up 4. Well, if you look at what happened here, if I was at negative 5, I ended up at negative 17. So when I went right 2, I ended up down 12. So down is key because down tells me the stretch factor, the A is negative. So whether you're going up or down is indicated by this. So I know the A value is negative. So now I'm just going to figure out what it is. This is what's happening. So that's what actually happened. Divided by what would have happened if it was just on the parabola, y equals x squared. Well, so we said it's what actually is happening. So negative, because it's down, 12. If I had gone 2 to the right, it should have been on the base parabola, it would have only went up 4, or down 4 if it was opening down, whatever. So this is 4. Well, 12 over 4, and I'm showing here, but many students, once they get the hang of this, they just do this in their head. They say, okay, it's down 12, it's supposed to be down 4, 12 over 4 is 3. Negative 3 onto x minus 3 squared, take away 5. So there's how you do it by inspection. And as I said, the key is you do this ratio. What is actually happening in regards to moving up or down based on how far you're moving away from the vertex, divided by what would have happened if it was just the base parabola. So our parabola went down 12, when on the regular parabola, y equals x squared, it really should have only went down 4. And that allowed me to calculate the stretch factor without doing the substitution. And again, this one, sometimes students find a little bit trickier, but if you can get your brain wrapped around how it works, it is a little bit quicker. Okay, so let's have a look at a couple more situations. So here's the first one, where I've got a picture in front of me, and I want to get the equation of this quadratic function. So it doesn't come right out and tell me, but I can read it from my graph. So the vertex would be at negative 2, comma 1. Now I need another point. So you're going to look this over now. You don't want to pick something like this because you'd have to estimate where it is, so that's no good to me. Find a point you can clearly see the graph cutting through. There's one there. There's another one over here. So this point is 1. 1, 2, 3, 4, 1, negative 5. Or you could have went with, what's this, negative 1, 2, 3, negative 5. Negative 5 would also work. Any point, doesn't matter. And if I pick this point, student B picks this point, we'll get the same answer. Doesn't matter. Okay, so let's go. Y equals A, x minus h squared plus k. Okay, I'll do it by substitution first. So substitution, remember this is x and y is the point, not the vertex, and then this is your h and your k. So fill those all in. So the y value is -5. Trying to calculate the stretch factor. The x coordinate is 1. Now if this is a minus, remember this is going to become the opposite, so that's +2 squared, and then your k value is +1. So we're going to take away 1 from both sides, -6a, 1 + 2 is 3, squared is 9, -6/9 is your stretch factor, so your function would be, reduce that, so -2/3 x plus 2 squared plus 1. Vertex -2 and 1, vertex -2 and 1, stretch factor of a -2/3, negative because it opens down. Now I'll show you that one if you did it by inspection. I'm not going to do them all by both methods, but I'll do a few here in the beginning just so you can kind of get used to the two of them. So here's method 2. So method 2, you go y equals, leave your a value blank for a second, x plus 2 squared, and then +1. And now you do the stretch factor by inspection. And remember, it's what is happening divided by what is happening on the base parabola. So I'm going right, let's see here, 1, 2, 3. So right 3 and down 1, 2, 3, 4, 5, 6. So there's what's happening divided by what should happen. So on a base parabola, y equals x squared, if you go over to 3, the y value should be 9. Right? Because 3 squared is 9. So what's supposed to happen is if you go right, it should be going up 3, or if it's opening down, it'd be down 3. So there's what is happening divided by what should happen on the base parabola. Look at over here. It's the exact same thing. And I did it by inspection rather than substitution. So then you just reduce this. Y is -2/3 x plus 2 squared plus 1. So you don't do it both ways. You do one or the other. And you don't try this one unless you really, really understand what's going on. If this is throwing you off at all, do it this way over here. All right. Example 2. So this one is just a table of data. So what I'm going to do first is analyze the data and see if I can figure out where the vertex would be. So what you're going to want to look for is what they call symmetry. Symmetry means that when you go the same distance to the right or the left of some point, you're getting the same y values. So I see that happening there. See how you got your 1 and your 1, 13 and 13. And my scale's all going by 1. So that's telling me that this point must be that one that's halfway between everything. So that's my vertex. Well, then you got a whole bunch of points to pick from. And remember, it doesn't matter which one you pick. So if I go y equals a x minus h squared plus k. So let's fill in what we know. I'm going to use, again, it really doesn't matter. I'll use this point down here, 0, 13. Just for the heck of it, when you're trying this example, pick some other point besides the one I do, and just to show you, you'll get the same answer. So the y value is 13. Trying to figure out the stretch value. The x value is 0. My vertex, so it's -2. That means it's going to be +2 in here. And the y value is -3. So this goes over here, 16. 2 squared is 4, so this is 4a. Divide by 4, divide by 4. Stretch factor is a, so our quadratic function that this is describing is y equals 4 x plus 2 squared subtract 3. And this time it turned out to be positive, which it should, because if you look at these y values, they're all above the y value at the vertex. So the only way you get y values above the one at the vertex is if it's opening up. If it opens down, all the other y values are lower than the vertex. And here it would be by inspection. This would be the last one I do both ways. So y equals, leave your stretch factor for a second, plus 2 squared and minus 3. And now pick any point. So let's say I go with, let's just go 1. So if I go 1 to the left, my chart is, I'm at -3, so this new y value is 4 above it. So what is happening divided by what should happen. Well, on a regular base parabola, if you go 1 left or 1 right, your y value is 1. So it would be 1. Y equals 4 onto x plus 2 squared minus 3. Same thing I got over there. Okay. One more. So this one I'm only going to do by inspection. And again, if inspection's puzzling you at all, you would do it by substitution instead. And I'm not going to draw anything. I'm just going to go y equals, so leave my a value, room for the a value. X, so my vertex is at 0, so minus 0. I really could have left it out, but that's fine. Squared. Subtract 3. Okay, so I'm going 4 to the left, up 37. Sorry, I'm at -3, and I end up at 37. So that's actually a difference of up 40. So what's happening is I'm going up, so positive 40. What should have happened, I went 4 units. Well, think about 4 units on a base parabola, y equals x squared. If x was -4, then the y value would be 16. So that should be 16. Now let's just clean this up a little bit. So 40 and 16 are both divisible by 8. So this would be 5/2 x squared minus 3. I don't need to put the minus 0 in there. There it is by inspection. Alright, so that just kind of shows you how 3 sort of different scenarios as to how you can take some information and use it to determine the equation of a quadratic function. So now we're going to get to the interesting part. This is where you can put this knowledge into actual practical application. I know sometimes some things in math, it's hard to see what would I ever use this for. This is what I like about this section. It's got some real nice practical applications to it. Okay, here's a picture of the St. Louis Gateway Arch. I don't know if any of you ever had a chance to visit here. I got to go there myself and a few other math teachers. I think it was back in 2007 maybe. And it was a national math conference, the NCTM it's called, and it was being hosted in St. Louis. So we actually got to go and examine the Gateway Arch in some detail. I've seen it lots of times. Anytime you see any kind of a sporting event or anything being hosted in St. Louis, guaranteed they're showing the Gateway Arch. Well, to my surprise, this is a massive, massive structure. And it's all made of stainless steel, and it actually has a tram system inside, so you can get in here. You actually go down underground, and there's like a little building or shop down here, and you can go up in this little tram. It'll take you probably to about here. Then you get out, and you kind of go up a few sets of stairs, and at the very top of this, there's an observation deck where you can actually get in there. And just off here to the right is Busch Stadium, where the St. Louis Cardinals play. So you get a great view of the stadium and the city from up here. So it was a pretty neat experience to get in there and go up into the Gateway Arch. Now, we're going to cheat a little bit. If you ever get a chance to visit the Gateway Arch in St. Louis, remember this discussion we're having today. The Gateway Arch is not actually a parabola. It's close, but it's not actually a parabola. Down here in their data or information about the arch, they say it's called something called a catenary, C-A-T-E-N-A-R-Y, which closely resembles a parabola, but it's not exactly a parabola. But for the sake of our discussion, we're going to assume or pretend that it is actually a perfect parabola. And we're going to use the measurements here to make an equation to describe the gateway arch. So in these situations, you're not going to be given points and ordered pairs. That's going to be up to you to make. So you're going to take a real life situation and you're going to put it on a graph. And the thing with this is you're going to be able to draw it anywhere you want. So if I draw it one place and you draw it somewhere else, our equations will be slightly different. But here's one thing that has to be the same. We have to get the same stretch factor. Everybody in the room, if there was 30 students in a class, in theory, every single student could have a different vertex. But every single student has to have the same stretch factor. You say, well, how does that make sense? I'll show you. The way you're going to start these is with a quick little sketch. So you're going to just, nothing fancy, quick little sketch. And you're going to draw this arch on an actual grid. So I'm going to make this arch right here. Now there's my St. Louis Gateway arch. Well, student B, who's sitting right next to me, they might have drew the graph this way and put their arch like that. Nothing wrong with it. Student C, for whatever strange reason, they might have drew their gateway arch down here. Student D might have drew it over here. It's completely up to you where you draw the arch. Now, some places are a little bit easier than others. Personally, I like to try and use the origin, the 0, 0 point, as much as I possibly can, just to make for some easier calculations. But there is really nothing says you have to put it in any particular spot. Okay, so if I go with where I've drawn it, let's see if we can figure out some measurements here. So it said that it's 630 apart. Well, this point right here is 0, 0. Well, if this is 630 feet wide, this would have to be the point 630, comma 0. Now, the vertex, this, would have to be halfway across this point. Well, half of 630 is 315. And then the y value at your vertex would have to be this height right here, 630 feet. So if I wanted to get my equation, alright, so now we're going to use this key information that we've found here. Let's just identify our vertex up here. So 315, comma 630. So now the numbers here are going to be a little bit goofier, obviously. That's okay. Y equals ax subtract h squared plus k. So this one I'll use the substitution method for. But you could easily use your inspection method. H and k, 315 and 630, and then this will be my xy. I'm going to use 0, 0. So y is 0, a is unknown, x is 0, subtract 315 because it's right 315, and then up 630. Bring this over here, so 0 take away 630 is negative 630. Now 315 squared, grab my calculator for that one. 315 squared is 99,225. Times A. So now to calculate your stretch factor. Negative 630 over 99225 would equal my stretch factor. So the equation of the gateway arch, fudging it a little bit and pretending that it's a parabola, would be, I don't know if I can reduce that, I suppose. 630 over 9925 is 2 over 315. It would be, now it opens down, so negative 2. This is just the reduced version of that. X subtract 315 squared plus 630. Now you may ask yourself, why would I ever want to do that? It doesn't even make any sense to do that. Well, here's what this allows you to now do. Let's suppose, for whatever reason, you needed to put some piece of metal or something, and you had to run it from the ground up to here, and let's suppose you were in 10 feet from the edge of the arch. So if you come over here to your picture, say, well, that would be right here, where x is 10. It's bad 10. And you're trying to figure out this distance. Well, if you knew the equation of that, if you know the x is 10, right, this is x, you should be able to use that to calculate the y value by substituting your x value in here. So now let's go over here and show you how you could use your function. So if I was 10 feet from one of the two edges of the arch, I should be able to calculate how high up in the air the arch is at that point. So y would equal -2 over 315, 10, take away 315 squared, plus 630. Throw that into my calculator, see what I come up with here. Let's see if it makes sense first. So I got -2 over 315, bracket 10, subtract, square that, and then add 630. Calculator says, I want the decimal version of it, 39.365. 39.365. That would be in feet. There's the exact distance from a point 10 feet from the edge of the arch up to that gateway arch. Okay, I've got a few more application questions. Oh, my picture disappeared on me here. There's supposed to be a picture with this. Oh, there it was. Okay, so you have a young lady standing. This is a train track here running through a train bridge. So it says that she's 1.6 meters tall. That's her height. She's situated 4.2 meters from the edge of the tunnel. We're trying to figure out how far is it from the top of her head up to here. This distance right, I can't see that color. This distance right here. So what we're going to do is take this picture, transfer it over here, and turn it into a graph. Alright, so let's see what I got. So I'm going to make the tunnel, as I said before, I like using 0, 0. So there's my train tunnel. I've got this point, which is 0, 0. This point over here, if this is 11 meters wide this way, that would be 11, 0. This is 14 this way, which means it's got to be in the middle. So if this is 11, half of 11 would be 5.5. So this point is 5.5, 14. There's your h and k. Y equals a x minus h squared plus k. So xy, any point on the parabola besides the vertex. I got two to pick from. I could go with 0, 0 or 11, 0. Either would work. And there's my h and my k. Let's fill those in. I'm going to use the origin, so 0 equals a, x is 0, minus 5.5 squared plus 14. Now, once you've got decimals introduced into your function, now you're free to work in decimals. You don't have to stay with the fractions. Bring the 14 over, so negative 14 would equal a. Let's square negative 5.5. 5.5. $30.25. So a is negative 14 over 30.25. Now this you can get a decimal for because decimals are in the question. So negative 14 30.25. I get a negative 0.463. Now we're going to, starting in pre-calc 11 and moving right through until we finish calculus, we're going to adopt the rule they use in what's called advanced placement calculus. Advanced placement is kind of a course offered worldwide where students can get university credit while they're still in high school. In that program, the rule is you always round everything off to the third decimal place. And that's where, if things do not go evenly, as a rule, from now on, you will always carry 3 decimal places and round off that third digit. So now, I am at negative 0.463 x minus 5.5 squared plus 14. So that's the function to describe that arch right there. Now, let's use it to answer the question. So the question said that if we came in here 4.2 meters, it said from the edge. You got to be careful. Sometimes this will say 4.2 meters from the center. Well, then you'd have to come this way 4.2 or that way 4.2. This one said 4.2 meters from the edge, which is going to make the x value 4.2. If it said 4.2 from the center, well, you'd have to take 5.5 and add 4.2, or take 5.5 and subtract 4.2. So the number here wouldn't actually be 4.2, but it is here because it said 4.2 from the edge, so I came in 4.2. We've got a lady standing here whose height is 1.67. Well, what we're going to do is figure out how far is it from the ground all the way up to here, which will just be, when x is 4.2, what is the y value? So once we get the y value, we'll know that distance. And then we're just going to subtract her height, and that's going to tell us how far it is from the top of her head up to the arch. Let's fill in 4.2 then for our x. Right, so x, there's x, 4.2. So y is negative 0.463. 4.2, take away 5.5 squared, plus 14. So I'm going to type this all in our calculator, and hopefully you're getting to the point where you can do that all at once. Much easier to do if you've got a calculator that lets you type on screen and see what you're typing here. So I'm going to put negative 0.463 bracket 4.2 minus 5.5, close my bracket. That'll be squared, and then add 14, giving me a y value of 13.218. 13.218. Now this would be in meters. That means the y, so the y value when x is 4.2 is 13.218 meters. That means from here, the ground, up to the arch is 13.218 meters. That's not what I was asked though. I was asked how far is it, or how much clearance, or how far is it from the top of her head, so from here to here. So this distance from here to here, we just figured out, is 13.218 meters. She's 1.67 meters, so to get this distance, which was what we're looking for, right? This distance here, well, that distance is 13.218 meters. Take away her height, and now here's the answer to our question. So I'll just get my calculator out again. 13.218 subtract 1.67, giving us a clearance above her head of 11.548 meters. That's the distance from the top of her head up to that tunnel, which we were able to figure out by just taking some raw data and a schematic, a scheme picture here that was given, turning it into a graph, and then analyzing that graph to find some measurements and functions. So as a mathematician, I really enjoy being able to take this knowledge and information that we have and apply it to this type of situation. I find that kind of a neat application. Alright, here's another one. So this is an actual picture I just grabbed from Google. I was looking for a parabolic tunnel under a road. So here it was. This is a parabolic tunnel that passes below the famous 401 highway in Ontario. So the 401 highway is the main highway that passes through Ontario. So the tunnel is 48 feet at its base. So this would be the base. There. That's 48 feet. A little slash like that means feet. It's 28 feet high at the center. So from there to there, it's 28 feet. Now we are going to try, and so you're the engineer working on a construction project, and you're trying to figure out if you've got some kind of a big oversized load that you're going to try and fit down through this tunnel, and you want to see if it's going to fit. They tell you that the building measures 18 feet wide and is going to be sitting 24 feet above the road when it's sitting on the float of a tractor trailer. You want to know if it's going to fit through here. Well, in order to give you the maximum clearance, you'd want to bring your load and come right down the center. You wouldn't want to be way over here to the right or way over here to the left, because then you're not going to have as much clearance. You're going to want to center the load and see if it'll fit in here. Well, if it's 18 feet wide, right, the load, that would mean from the middle, you're going to go over 9 and over 9. That would give you your 18 feet. And then what you're going to want to figure out is how far is it up to the arch? How far is it up to the arch? And this is a real practical application, because obviously if you're a construction crew and you're trying to move a big heavy or a big oversized load, you'd want to know whether it's going to fit through this tunnel before the day of when you actually arrive there. Like, these things have to be planned out. Well, to help us do that, we're going to put this tunnel on a graph. So here's my tunnel. We said this point would be 48, 0. I'm going to put the left edge of the tunnel at 0, 0. The middle of the tunnel would be at 24. It told us the height of it was 28, so 24, 28 would be your vertex. Just for the heck of it, let's do this one by inspection, just for those inspection people. Now, if you're not doing it this way, that's fine, but you'll have to do a bit of extra calculating. So I'm going to go x minus 24 squared and up 28. Okay, so my stretch factor, it's opening down, so I know it's negative. I'm going right 24. No, sorry, from the vertex, I'm going, let's say, left 24 and down 28. So it's what is happening divided by what is supposed to happen. Well, let's think about it. If I go 24 left or right of a base parabola, y equals x squared, the y value should be 24 squared. So I'm going to go 24 squared is 576. So this is negative 28 over 576. Now I'll try and reduce that. Hopefully you know how to use the fraction button on your calculator for reducing fractions. It really speeds that up. So you just put in 28 over 576 in your calculator using the fraction button, and you just hit the equal sign. And it does reduce to 7 over 144. It opens down, so it's negative 7 over 144. Okay, so now this is where the thinking comes into it. I've got my load here that is 18 wide. Well, that means you're going to want to center it, which means you're going to go 9 this way and 9 this way. So if you go 9 to the right of 24, you're going to be at 33. If you go 9 to the left, you're going to be at 15. So you're going to pick either 15 or 33, your choice, doesn't matter. You're going to fill that in as your x value, and you're going to figure out what is the y value. And once you figure out the y value at either of those 2 points, you're going to know what you've got for clearance here. And then, if that number turns out to be more, how high is your building? If it turns out to be more than 24, you're good, because that'll mean that the tunnel is going to be higher than the load. If your y value turns out to be smaller than 24, then that building is not going to fit through the tunnel. So here we go. We're going to fill in, I'm going to use x as 15. Y equals negative 7 over 144. x is 15. Take away 24 squared plus 28. Put this in our calculator and see what we get for a height. Negative 7 over 144 bracket. Sorry folks, a bit of a technical glitch, but I got it back here. So it gave me an answer of 24.063 feet. Now what does that mean? So if you look over here, that means that when x is 15, so I put 15 in here for the x, right, that was 15. It gave me the y value, meaning from here up to here, because the y value is 24.063, that means that there's 24.063 feet of clearance. We need 24 feet. So luckily it will just barely fit through the tunnel. Now you have you only have like 0.06 of a foot to spare, so that's not very much. There might be one of these scenarios where when the tractor trailer pulls up to this, they might have to deflate all the tires down so it drops it down an inch or two to make sure you get your clearance through there, because it's really, really close. However, the mathematics behind it says that it should fit. Alright, now we've got one more that I want to look at. This one deals with a bridge, and it's a bridge out in Vancouver called the Lions Gate Bridge. Here's a picture of the bridge. Now you have to read and interpret. That's part of math as well, but sometimes students will struggle with that. So I'm going to read this. I was talking about there's two main cables. That would be here, and then another one on the other side of the road, or the other side of the bridge. There's towers. That would be these two things. These are your towers, and they are 111 meters tall relative to the water. That means from the water, so we can see better. So from the water up to the top of this tower is 111 meters. This tower is the same. There to there is 111 meters. That's what that says. The two cables are 472 meters apart. Well, that means from tower to tower, here must be 472 meters. The lowest point of the cables, that's right here, that's the lowest point, your vertex. From the water up to there is 67 meters. So part A wants us to come up with a function, that would model this situation. So let's get a picture of it first. I should be able to fit it here, I guess. So I'm going to use the water to be my x-axis. So this is water level. Now let's put I want this cable to then be modeled on my graph. So I'm going to start it at 67, and then it's going to go up to 111. And let's put the left edge, so here's one tower. That's the top of one tower. Then when I go over here, 472 meters, I should be the top of the other tower, which means the middle, or the lowest point of the cable, be half of that, 236. And now you got a cable that looks something like that. I want the equation of this graph. Well, I know the vertex. The vertex is at 236, 67. Now somebody else might draw this differently, so they might have a different vertex, but as I mentioned earlier, we have to get the same stretch factor. When I get another point, I'm going to use this point up here. So this point would be the ordered pair 0, 111. That's my second point that I'm going to use to calculate my A value. Y equals A x subtract h squared plus k. Vertex form. Fill in everything that we know. So we know xy. We're going to go with 111. A is what we're trying to calculate. The x value is 0. The h value at your vertex is 236. squared, and the k value would be 67. Okay, so I'm going to rearrange this. I got 111 to subtract 67. Calculator going here. 111 subtract 67 is 44. Negative 236 squared, so 236 squared is 55,696. That'll be multiplied by A. Now I want to calculate the stretch factor. A is equal to 44 over 696. I'll just check on the fraction button on my calculator to see if that will reduce any further. So 44 over 55696 equals, oops, didn't work. Try that again. 44 over 55,696 equals 11 over 13,924. All right, let's write out our equation then. Here's the answer to part A. Y would equal, it opens up, so it's positive 11 over 13,924 x subtract 236 all squared plus 67. Alright, now we're going to use that function to answer part B. It says determine the height above the surface of the water of a point on the cables that's 90 meters horizontally from one of the towers. I'll go to my diagram then. So basically that's saying come in here 90. Well, on my graph here, that would be to the right of this tower. There's 90 horizontal. So I'm going to substitute that in as my x and then use that to calculate the y value. Right, so if I go 90, comma, figure out y, that will then give me the distance, because this is the water, from the water up to the cable. So it's nothing more than substituting x as 90. Whoops. So let's put that in. So y is equal to 11 over 13,924. X is 90. Take away 236 squared plus 67. Let's see what we get for a height. Alright, so that 11 over 13,924, 90. Don't have my glasses on here. I'm having a hard time seeing these keys. Minus 236 squared plus 67. Looks good. What do I get? 83.839, so that rounds off to 80. Remember, we're going to go 3 decimals. Although I think it said up here. Let me look at this. Yeah, it says nearest tenth. So nearest tenth is 1 decimal place. So 83.8. So what we've just figured out is that if you go in here 90 meters to go up and hit the cable, which was the parabola in our graph over here, the answer to their question was 83.8 meters from the water up to the cable. Alright, so we're going to stop there. Hopefully you've gained some insight into how to find the equation of a quadratic function. Some of this you would have maybe seen before, but regardless, now you're going to go to your class notebook, find the practice sets of questions, and you're going to work through those as best you possibly can. If you run into any difficulties, you can ask about it either in class or send me an email and put the question in your feedback section, or I think it's the need help section of your class notebook, and I'll try and get you pointed in the right direction. Alright, best of luck, and see you in our next video.